Wonderful.
Great.
So let's start. Let me briefly introduce our speaker today. Thanks for coming. It's my great pleasure to introduce Junyu Liu, being here with us today, getting up very early. Sorry about this. Who will speak about a subject that's close to our heart, namely on representation learning via quantum neural tangent kernels. That's a subject that he recently got interested in. He comes from China. He has done his his bachelor degree at the University of Science and Technology of China, but then moving to the United States to do the master's degree and the PhD at Caltech, to now work in Chicago with the uni there, but having a joint appointment with IBM as well. Most of you have already heard of Junyu's work in several flavors and ramifications. He's prolific in his activities. So on his webpage, he states that his work has applications in optimization, machine learning, data science, big data, quantum computing, computer science, string theory, particle and nuclear theory, black holes, gravitation, cosmology, statistical mechanics, from formal theoretical predictions, simulations to observations and commercial realizations. And that's no over-exaggeration in that there's one paper on each of these subjects. He's quite a machine. So we are even more looking forward to your talk and what you have to say. Thanks for coming, and the stage is all yours.
Okay, yeah, thank you very much for trying to test the sharing the screen.
Please do. There's no obstacle, I think.
Okay, good. Yeah, can you see it?
Well, yeah, I mean, almost. It's not full screen yet, but it's getting there.
Right now it should
wonderful.
be full screen. Yeah, okay, great. So thank you very much for inviting me here, and I'm glad to give a talk. So as introduced by James, that I have a very broad interest. So I'm graduated from Caltech in this year, and right now I'm a postdoc in Chicago and IBM. And it's a joint position. And I have a very broad interest that I used to have a high energy physics background, but now John Prisco is actually one of my advisors. So, and then following his path, I sort of adiabatically moving and from high energy physics to quantum information science and quantum computing. So right now I'm working much more on quantum information science, and also some related question about machine learning. So today the topic of my talk is about quantum representation learning, a theory of the quantum neural tangent kernels. So those are my founding agencies: the University of Chicago, IBM, and the Molecular Engineering Department of U Chicago. And there is a new organization that is called Chicago Quantum Exchange, and also the Kernel Center for Theoretical Physics. So today I will present a work that is already appearing and another work in progress, together with people in IBM and U Chicago, with mentors Liang Jiang at U Chicago and Antonio Mazzucapa at IBM, and Francisco Tacchino and Jennifer Glick working in IBM. So that's all about the introduction. So maybe I can start from a generic introduction of quantum machine learning and what I'm thinking about that. And then later I will move to some more technical part of our work. So quantum machine learning is a new area that is in development, but it's very promising, but it is still kind of unclear. So as to very promising technologies like machine learning, AI, artificial intelligence, and the quantum computing, and they are very promising, and it's natural to think about how to combine them together. However, people still have some big picture problems. Firstly, we wish to define what is quantum machine learning. So different people might have different models. So, and furthermore, we wish to ask why we do quantum machine learning and where is the quantum advantage. So why you are doing the quantum machine learning instead of their classical ones? And also, what is the typical problem for quantum machine learning? So what is the flagship application that we are looking at? And also, what is the quantum database that corresponds to quantum machine learning? Database means a training set we are going to use. Maybe we are able to create a database. It might be classical, it might also be quantum. And also, what are typical quantum machine learning algorithms, QMIO algorithms? So those are not completely known yet, although already people, maybe some of you already have some answer to those questions. And we already know, but we definitely know something about quantum machine learning. So firstly, how to encode the data to the quantum devices that solve partially how to compile your classical data and from a classical database to the quantum devices, which is very important for the learning process, is given by the so-called quantum random access memory, or QRAM. So that has been QRAM that has been proposed a few years ago, and solves the input problem, partially solve the input problem. And for the output problem, recently people discuss shadow tomography a lot from the Scott Anderson's work, and also by Huang and Kwong and Friskill, very recently, that about how to extract the output information from the quantum devices. So that is a tomography problem that partially solves this extraction of the output information question. And in the middle of the algorithm, people already know how to solve the linear algebra problem, for instance, by considering the inverting the sparse matrix. People know the celebrated HHL algorithm. So that tells you how to solve the linear algebra problem in a quantum device with a sufficiently significant amount of quantum speedup. So those are some of the reasons that we might consider quantum machine learning as important application of quantum computer in the future. So
in the near term, will you say more about the shadow estimation problem? Because of course, there's also the interesting thing that this allows to provide insights into like classical notions of machine learning applied to quantum experiments. Will you come to that later, or?
Yeah, no, I mean, this is just a big picture introduction.
Okay,
and
wonderful.
yeah, people, and what I'm referring this is that especially the usage of shadow tomography in the recent work of them, that by showing the difference between the classical and the quantum complexity using statistical learning theory, and this is what they did recently, and by defining different input model of classical and quantum, and using the tool about shadow tomography or similar to it, and the people show that there is an exponential separation at some cases. This is what I mean here, but here I will not talk about shadow tomography today.
Okay, wonderful.
For most of the time.
Okay.
So then let me move to the primary architecture. I will look at people I think in this group are already very familiar with. So they are given by some variational analysts on some Pauli operators, given by also by some constant gate in the middle, and there are many of them, and you could train those classical variable theta L and using some loss function and do it in a quantum circuit. And this is famously known for instance, variational quantum eigensolver VQE, and also some other problems in this quantum computational chemistry, and also including QLA and also quantum neural networks for a learning problem. So those are already considered to be possibly important application. And then, but people still don't understand quite well how it works theoretically, or when it can work or cannot work. So this is given previously people have discussion on the so-called barren plateau, and which is sort of a no-go kind of statement that considering that so how you could train those variables for large dimension of the Hilbert space, where sometimes you will find that this variational angle does not move if you assume some Hart random or sufficiently close to Hart of your variational circuit. So that is some basic statement about variational quantum algorithms. But today, what I'm doing, and today is going to answer maybe part of the problems by so-called theory, which is called the neural tangent kernel theory, that is originally happening in the classical machine learning community. But using that as a tool, we are able to build an analytic theory of quantum machine learning, and from the first principle, and we show that there are some cases where you could provide the exact guidance or exact prediction about the gradient descent dynamics. I will explain what this means by quantum version of neural tangent kernel and those what does this mean later. I will describe it later. But generically, what we are going to solve in the theory, partly at least, is firstly how to choose variational ansatz and which kind of variational ansatz is good and which kind of variational ansatz is bad. And also, before the training, we want to know, at least in some cases, how good the convergence will be. And in some cases, can we give analytic predictions? And also, what does the gradient descent dynamics look like? Can they converge or so what is the conceptual or technical difference between quantum machine learning and classical machine learning? So I hope that based on our theory, we will answer some of them. And especially I will add here how to understand properly the barren plateau problem. So this is the outline of the They briefly talk about quantum neural networks that you might be already very familiar with, and then I will talk about a neural tangent kernel theory, and then I will discuss how to build a neural tangent kernel theory in the quantum analog, and also I will discuss the so-called frozen neural tangent kernel and the quantum meta kernel in some limit, and later I will give a comment on the so-called large width limit and its connection to the barren plateau problem that is related to our currently ongoing work. And finally, I will give some conclusion and give you a set of open problems that people might think about. So until now, do you have any questions? Okay, great. Okay, so let me start quantum neural networks that I think most of you are already familiar with. But let's give a warm up and give a brief overview. And as I introduced before, this quantum neural network is that you have some constant gate in the middle, but primarily there are some trainable unitary operations that are given by parameterized by e to the I theta x, where x might be some simple like 2 qubit Pauli or some Pauli or some gates that you could relatively implement it easily, and it might have some generic, geometric structure, or it might have some localities there, for instance, some sort of convolutional construction of quantum neural networks. But here I want to keep it general, that it's we want to make a general as a set of constant gate and trainable gate. So, and later I will also briefly discuss this so-called hybrid quantum classical network, which is that in order to see clearly what's the difference between quantum and classical, I wish to merge these two together. What I did is that I created a feature map, and from the classical data, I want to put it into the quantum circuit with some trainable parameter theta, and then I do the measurement, I get output, and then I put it into a classical neural network with some weights and bias, and then I merge it to the quantum feature map again. So this is, some people call it hybrid quantum classical network that combines the construction of quantum and classical. But this is just a theoretical model that I will briefly discuss later to show some properties that connecting quantum and classical. But in some sense, in many cases, I will just describe this quantum model purely in general.
Wait. So this is a multi-round scheme, right? I mean, you have the classical neural network and the variational quantum circuit, but you have many rounds, and I mean, there's no measurement along the way. It's just one measurement at the end. Is that right? Or
So when you are transforming from your quantum data to a classical data, you have to extract the information.
okay, sure. That's what I'm
So
okay.
in
That's
that
why I
case,
was.
you might need measurement. Yeah,
I
in
see.
that
That
case.
was my confusion. Okay, thank you.
Yeah, so great. So and then you could perform the same like gradient descent dynamics as the classical networks by making this analysis and measure something that you are interested in. For instance, this is a simple, I mean, numerical example, which does not converge very well, but it's in some example or test that you could do in by using some IBM setup, and in the IBM Q-skate simulation that we try to do some example, but you could do it. And so it's very common that people the some gradient descent dynamics and in very different cases. So then I will give a brief introduction of neurotangent kernel theory and this so-called large width limit. So the theory can be briefly summarized as the following. So here we specifically consider this mean square error loss. So which is the square of y minus z, where y is the data label, and in the supervised learning scheme, and z is the output of the model. And then we give a square of them, and we make a sum. So this is the earliest loss function you have learned in, for instance, the linear regression. And then you could write the difference between the output and the data label, and which we call it the residual training error. It's a term in a linear regression as well. So, and then to study this systematically, we could put some analytic formulas here. So we measure the difference between two time steps, which D, this fancy D, means the difference between time step T plus 1 minus time step T, and the difference between them, and for some observable O, for some some quantity O. And then this acting on theta is given by the gradient descent formula, and is the simplest version of the gradient descent. You might consider more complicated ones, but here I'm doing this basic construction. And then what you could do is that you could go a little bit step back, that when you compute the difference between the variational angle theta in the limits where the learning rate is sufficiently small, this does not change that much. And then you could try to use the simple linear analysis or the simple calculus to plug this back to the residual training error or the output. And so what you get is the following. So because you put this back, so this becomes a matrix that is acting on a vector. So the matrix is given by the event space, which I call alpha and delta, and also the output dimension I and I prime, and making a derivative, which is from this derivative, on the variational angle theta. And you have two of them, and times them together, make a sum over all possible variational angles. And this is a matrix which people call it neurotangent kernel. So this formula can be understood as a matrix established in the event space of a training set that is acting on the residual training error and as a vector in the event space. And then you make a sum, and this is a calculation you could do in the linear approximation as a first order of eta when sufficiently eta is sufficiently small, and it's just a result of the calculus. Okay. So that is a definition of so-called neurotangent kernel. But how is this useful? So you could actually already see that if this guy is a constant, if this is a constant, if you change this z to be epsilon, because they are just simply linearly related. So if you change this z to epsilon, and if this guy is a constant, then you get a gradient descent equation, which is analytically solvable. So this is something like the differential equation. D epsilon is equal to epsilon times a constant, and then the solution is linearly exponentially decreasing. So this is what we learn from the first order differential equation in your basic mathematics course. So you could already notice something that's analytically solvable. And however, in the most case, the neurotangent kernel is not a constant, but it could be some constant in a general setting. So let me describe some theorems about neural tangent kernel for classical neural networks. For which we consider for the classical setup, we consider the multi-layer persistence, which is the simplest one that people usually consider for the artificial neural network. And in the large width limits, the neural tangent kernel is approximately constant during gradient descent. The whole gradient descent process and the correlation function of the neural outputs are approximately Gaussian. The perturbative correction is given by a ratio, which is the depth divided by the width. So if you, this looks very complicated, but let me explain you in relatively simple terms. So let's make a simple analogy of quantum field theory or quantum mechanics. So the width is the definition of the width in the classical setting is the number of neurons in each layer in the simple MLP model, and the depth is given by the number of layers. So for instance, and here you have a 3 depths classical circuit, and where you have width 5, 3, 2 in the first few layers. Okay, so this is just a basic definition of multiple layer precipiton and width and depth. And then this large width limit is similar to the large N limit in the large N gauge theory. If you talk about quantum field theory, and the depth divided by width ratio could be simply give an analog of the coupling constant, which is the called tooth coupling in ADS-CFT. And the wide neural network means it's a weakly coupled theory, which means that the neurons does not interact that much, and there are so many neurons that are highly overparameterized in each layer.
But can I ask a question about this?
Yes.
So this I love this analogy. That's really cute. But I mean, at the end of the day, it means that this wide NN limit is like basically like a perturbative limit, so that the structure of the argument is basically that of a central limit theorem. Is this right, or like
it's partially right? Yes. So it is a result of the central limit theorem, but I mean it's also a result that because it may not be always the case. For instance, if you are overparameterized but you have many depths, not the width, you will not have that phenomenon. So even if you have many parameters, but they may not exactly be Gaussian if you don't put them into width. But instead, you put them into steps. They may not be. Exactly Gaussian. So in that case, we could use as I described before. If you have sufficiently wide neural network, it is like the weak coupling, and for the deep neural network, it is strongly coupled. And the theorem is under a few assumptions. So firstly, the learning rate is small. Otherwise, I cannot precisely define my neural tangent kernel. As I showed you before, that you have to use the small learning rate approximation. And secondly, you are averaging over weights and bias when initialization. So what it means is that the correlation function I'm talking about here is an average over an ensemble average of weights and bias when you initialize your neural networks, because you are most possibly to put your weights and bias to be some random numbers. And then the correlation function of the neural outputs will be approximately Gaussian according to the ensemble average of weights and bias. So that is the setup of the theorem. Okay. And until now, is there any questions? Okay, great. So then I'm happy to talk about a quantum version of a neural tangent kernel theory. And many of the steps becomes already pretty straightforward, but let me just go from step to step. Okay, so firstly, you could consider the optimization problem, or just like the Hamiltonian simulation problem, where you are going to solve your so-called BQEs, and then you make some analysis, which is some variational gates and acting on some fixed state, and then you are measuring some say ground state energy of the Hamiltonian or some operator or something, and then you make a mean square loss. So importantly, I have to use the mean square loss here, otherwise our nice theoretical property will break down. So we have to use the mean square loss so to make this theory work. Okay, so assuming the mean square loss, And we could similarly define a residual training error, and then we do the same calculation before, and we get the residual training error, which is the error of what we are training by this toy version of the neural kernel, because right now there is no training data, or you could consider this O0 as a training data, or it is just a trivial one-dimensional case. And in this case, and the neural kernel is a number. So instead of the matrix. So this makes the problem much simpler, and you could think about it just directly. And then you could actually compute the neural kernel and directly from some given answers. And if you write your answers like this, and then you could derive some analytic formulas which are given by this. You already know this before you are training. So actually, so you could do this computation and into some Python or Mathematica, and you just get the result. And importantly, right now, this neural kernel is highly nonlinear. So in the variational angles, when I'm talking about not linear or nonlinear, I'm just talking about linear or nonlinear with respect to the variational angle, which is a training parameters. So this is a
linear. You mean, sorry? So linear in the thetas, you mean, or?
Linear in theta, not in feature. So it's linear just in variational angle theta, not in feature. It will be more like a difference, more difference when you talk about the learning case. But right now in this toy example, there's no feature map. So the feature is a constant. And because we don't have the training data yet. And when I'm talking about linear case, I'm just talking about this is a linear in the variational angle theta. And K is highly nonlinear in the variational angle because all those things are depending on your initial variational angle theta. I'm not performing an average of them yet. So this is a feature of so-called representation learning. Which is a feature learning that during the gradient descent that your kernel is changing, and the effective kernel, which is the neural kernel, is actually changing. And that means that in some sense, an abstract notion of your feature is changing, even if you don't have a definition of your feature map. So that is a property of your, in the classical sense, the representation learning, which is naturally from the nonlinearity of the variational quantum circuit, I would say. So in that case, you will have the representation learning features. And you can move this setup to the machine learning problem by just considering a feature map, and you map the training data or your event space and directly to a feature map, and then you try to construct some output. Typically, we do it in the unitary way. We measure some observables, but you could also do it in the amplitude estimation, where we also do that, which is complex. But in this case, this is a real output, and then we could define the residual training error, and similarly, and also the mean square loss. And right now, this neural kernel is really just a matrix instead of a number. And then you could keep an eye on this prediction as well. So by directly do this computations I mentioned before by giving this answers. And similarly, and you could actually prove that in this case, the neural kernel is always positive, semi-definite, and symmetric. So which means that it has to have the positive eigenvalues. And the number of eigenvalues, if you are in under-parameterized region, it is equal to the number of variational angles you have. And in the over-parameterized region, it is full rank. It is not a sparse matrix, a full rank matrix where all the eigenvalues are positive.
And
so
again, the reason for this is that it's just basically a sum of like A dagger A type terms, right? It's like
right.
conjugate of the okay.
But in general, so it's part of because of this construction that it is this already has this nonlinear form. Yeah. Yeah, so again, so K is highly nonlinear in terms of theta. This is a feature of the representation learning. And then I will talk about.
I actually have a question about the previous slide. Could you briefly explain what is actually the meaning of all these U's and W's?
All this what?
the U's and the W's in the expression?
Right now, I just want to keep it in general. So W is a general constant gate, for instance, C naught gate, when you're doing the variational simulation. And this W is a general constant gate, and X or U is equal to this, UL is equal to e to the I theta X. And this is the trainable gate you have to set up in your rational answers. I want to keep it general. As long as you give me the formula of your rational answers, I could compute the neural tangent kernel for you. So, but it's a very general formulas that, for instance, you could put the most popular like UCC answers in quantum computational chemistry, and then I can tell you what the neural tangent kernel could be.
Okay, thank you.
Yeah, great. So, and then I will go a little harder and talk about in some limits, the neural tangent kernel and the meta kernel. So before we talk about the large width or averaging over the rational answers, let me talk about a simplest thing, which is about the observation of a constant or frozen neural tangent kernel in some limit. It is actually a generic feature, even not related to the large width that I'm talking about before. It happens generically when the gradient descent is slow enough and the trainable parameters do not vary too much. If your theta is not changing that much, you are basically stopping your training. And then in that case, where people call it lazy training, and then you are already able to, see approximately constant neural tangent kernel in this limit. And then you could actually do the perturbation theory that is around the end of training, or this late training that might happen at the end of your training process if you really get the convergence. So this is a generic feature, not just the neural tangent kernel. It's just in the large width. It just says that in general, when your rational angle does not move that much, and then you are able to have the approximately constant neural tangent kernel. And then you could do some perturbative expansion and using the theory, and then that will tell you some property about the convergence of the neural network, quantum neural network at a late time. So this is what I mean by this plot. So in general, in the gradient descent dynamics, and there is a cat here, and which represents the quantum state, and then you could define a quantum version of neural tangent kernel associated with it. And in some limits, and we're maybe at the end of training or some other cases, and the cat is stopping moving, and which means that it is frozen, and then it almost does not change so that much in terms of residual training error. And then in that case, you are able to do some analytic predictions. But in general, it might have some highly nonlinear property. Then if we don't take any limits, it will be highly nonlinear. So is this clear?
To be honest, no, but I have a very naive question about this. So, intuitively, this limit, is this basically like a perturbation around the local optimum, so that you can say that in the vicinity of a local optimum, you are guaranteed to be converging, and the assumption that you need to be close to the optimum is basically hidden in this limit that you're having? Is that right?
Right. Yeah, it's true. It's true.
Good. Then
so in this case, we could try to, this neural tangent kernel is a constant and you can compute it. And in this case, you will have a guaranteed convergence around the end of training. And if you are doing the perturbations, as you said, and then around the end of training, if you assume that the kernel is a constant, as I described before, it will have some analytic predictable exponential convergence, so that it will be e to 1 minus eta times k as a kernel matrix to many time t, and then you times the matrix many time, and it will be exponentially converge. And you could actually do this compute this neural tangent kernel in your real simulation. And these are some, examples using the data device simulating the real IBM data. And then we take a classification example, and then we try to compute the gradient descent dynamics and compute the eigenvalue of your neural tangent kernel. And we find some convergence at the end of the training, even if sometimes it is noisy, but it's still kind of convergent for those eigenvalues. And in those cases, we are able to say an exponential suppression, and we in fact observe it by just directly computing the neural tangent kernels. So, but this is at the leading order, but you could, of course, do the next leading order perturbation theory. So this is the method is given by this, the prediction is given by the so-called quantum meta-kernel, where the meta-kernel is defined by a higher order, a little higher order of the predictions, and which involves the second order derivative of your prediction. So this is something like the neurotechnic kernel, which is just a first order, but you have a second order here, and this object is also sort of a kernel that we call it quantum meta kernel. And then this thing is also could be regarded as a kernel, and you can actually analytically solve the solution. And the convergence is a little bit more complicated. You could decompose the residual training error on the training set by the free part and the interacting part. And then the results will be predicted and bounded by this kind of formula, where which is not exponential, but a linear thing that times exponential. So it is a little bit larger in scaling, but it will finally converge and give you 0. So this is many of those results are a combination of quantum architectures, and also this book that tells you how to compute this so-called meta kernel in the classical setting. And this is so-called the quantum. So there are some terms, complicated formulas by tensor contraction. These are called quantum algorithm projectors. So the existence of the quantum algorithm projector is an indication of so-called algorithm independence. And that means that the model, and which is beyond this neurotechnic kernel limit, and or the frozen neurotechnic kernel limit, it will have a little bit difference and between global minima and the local minima during the gradient descent. You have multiple solutions around them, and then that means that the solution, the method to find the solution, that depends on the quantum, the algorithm itself. So it is a feature of so-called algorithm dependence, and also a feature of representation learning. So let me comment further about its connection to the large width. So there is, let me just firstly show you a heuristic formula. So this is the initialization of classical setup, where you consider lots of weight metrics and we make an average. We make an ensemble average of weight metrics when we are doing initialization. This is called Liquin initialization, which is the standard one that people did. And then this is given by some constant, which we set, and divided by the dimension of Hilbert space. It is just a dimension of which is divided by width, and which is just an initialization. But it is very similar to the quantum one design formula, and it could be also regarded as an initialization, where this width is replaced by the dimension of Hilbert space. So later I will go.
Sorry, question. I mean,
yeah.
to me, it doesn't look similar. It looks kind of identical, but it's not quite identical because the W's are not necessarily unitary, or what's the?
Right. So right. So W is not unitary. This CW is a constant that you are.
That's basically like a non-unitary potential expression or something like that.
Right. So in order to have the correct scaling of the output, the classical neural network have to make it to be suppressed by the width.
Okay.
And then times the constant. The CW is an order 1 constant, and this is suppressed by width in order to make sure the correct scaling. There are some other scalings as well, but I will talk about this later.
Wonderful.
So in order to, at the beginning, in order to see a direct connection between quantum and classical machine learning, so we could look at the hybrid model of a quantum classical neural network, as I introduced you before, that has a redundant encoding and decoding process. So we could notice that the width in our model is defined right now by the number of classical variables. So in this sense, and the classical definition of width is actually the quantum definition of the circuit depth. And that is upper bounded by the dimension of the Hilbert space in some sense, because the independent output that you are able to extract from the classical circuit, from the quantum circuit, is upper bounded by the Hilbert space. So actually we have proven a similar non-Gaussianity theorem that is similar in this architecture, that is kind of similar to the classical setup, that if you consider the setup of the classical output, and which is something like this, and then if you assume that this thing is true, and sorry, so if you have assumed that the following quantum architecture requirement of the 4-point function is true, then you will apply that it will give you the consequence that the output of the classical neural network in this setup at the end will be suppressed by one of the dimension of the Hilbert space. So in some sense, the width here is serving as the dimension of the Hilbert space. In some sense, as long as this quantum output and has some classical property, has some orthogonal property that, sorry, there is a typo, alpha omega is alpha 1, alpha 2, and alpha 3, and alpha 4, 4 different independent events. And as long as they are sufficiently orthogonal in the following sense, where their quantum output indices has a delta function here times the order 1 constant. So as long as this assumption is true, and then you will have a guaranteed non-Gaussianity theorem that is similar to the classical case. Maybe it is a little confusing, but let me just make a few comments about this, because this is closely related to our ongoing work on how to make a Howard random average of those variational circuits, and we get some very interesting results that has closely connected to the barren plateau, but I'm not going to talk about today. And also, especially please make it confidential, that in the sense that this is something that we are working in progress, and we can talk further in person after recording if we want. So this orthogonal condition that for the quantum output I will talk here could be naturally satisfied by sufficiently random Howard answers that, as I mentioned, this is something like the orthogonal condition that is similar to the Howard random formula. So one might bring ourselves to the large width limit if we have a sufficiently large Hilbert space dimension which will allow you to bring you to a larger width or larger circuit depths. And then I will I mean, it will be interesting to say that, for instance, how this width is comparable to the dimension of the Hilbert space where we are at the over-parameterized region. And if it is not the case, it will still provide you highly nonlinear regime, which is a feature of representation learning. And this phenomena has a deep connection to the barren plateau problem that I will talk maybe in some future series of talks. This is related to some of the work that we are doing in progress. So again, this is an analogy that I talk about today. That is to set up and suggest a connection from quantum classical, from the large width theorem in the classical machine learning to the quantum setup of Howard random formulas, and also the barren plateau problem that has been proposed like 3 years ago. Okay, so finally, so do you have any questions at this point? Okay, good. So finally,
some ideas, but that's for some other time, not for today.
Yeah, not for today, right? Not for today. So finally, I will give some conclusion and also the open problem. So for a classical contribution of our work that is beyond the quantum, that purely you could regard our paper as a classical paper in the sense that we make some contributions that we give a complex generalization of the classical neurotangent kernel theory, because quantum mechanics is complex. Just now I showed the real case, but in our paper we systematically also discuss the complex case as well. So furthermore, we discuss the first frozen neurotangent kernel and meta kernel calculation in the lazy training process I described you before. And furthermore, we have a discussion about the different scales of initialization of the classical large width limit, where this is so-called clean initialization, but there are another initialization, which is called NTK initialization. Both of the initialization work. And we have some discussions about those different type of initializations. And purely beyond the quantum community, but purely in the classical setup. And furthermore, there are some open problems. Firstly, is that we are able to provide the concrete guidance at this stage already to the practical guidance of variational quantum algorithm. And furthermore, we are able to study it using, for instance, using some ODE theory. So this is the idea that people could consider working on, because this kernel do not take limits, and in general they are highly nonlinear. So you could study them in the perspective of the ODE theory, and then that could tell you maybe some guidance about which kind of rational analysis is good and which kind of rational analysis is bad. And then there is a connection to the barren plateau problem that I'm pointing out just now. And furthermore, there is an effect of quantum noise that you might consider. I already showed you some noisy pictures just now, but for the effect of the quantum noise, it is not considered by the classical people, of course, because they don't have that much noise. But in the quantum case, it will be interesting to investigate how to make this neural tangent kernel to be adapted with the noise that you could consider, when you are building your theory. So I think that is all of my talk today. And then until now, do you have any questions?
Wonderful. Maybe let's clap for now. Thanks for now. Thanks. That was a great talk.
Yeah, thank you very much. Yeah,
so much. We had lots of questions along the way, but maybe that's a good moment to take a couple of more questions.
Yeah. So, do you have any questions?
I have some, but I mean, I can also swallow some and let have lots of people ask questions. And I have a kind of detailed question. When you mentioned this kind of Gaussian convergence, I was a little bit reminded of these random deep neural networks converging to simple functions, a la De Palma and Seth Lloyd and so on. Is this a kind of related phenomenon? Or?
So it may not be the same, but I'm happy to take a look. But I mean, the deep neural network and the convergence to Gaussian, and is that in a classical setup or is it in a quantum setup?
I mean, there was a follow-up in the quantum world, but as such, it was a classical statement.
Then it's probably the same. So it's a hot topic in the theoretical machine learning community in recent years, and people discuss a lot about the Gaussianity, but not really for the deep neural network, but it might be both deep but more wide. So
it matters how you take the limits, right? So
yeah. So it is a coupling. So I have, honestly speaking, I have not heard of that Seth Lloyd's work about this, but the point is that so here it is there is a definition which is a coupling and between depth and width, and then you could take this coupling to be small, and then you are in the perturbative regime, and when the width is sufficiently large, but depth could also be large. It could be both deep and wide, but it has to be more wide than deep. And in that case, you will have the Gaussian correlation and also convergence, exponential convergence, similar to the classical linear regression.
Mm-hmm. Okay, good. Interesting. More questions?
Yeah, so there's a question in the chat, or maybe not. So, okay, so if no questions, and then I can stop sharing the screen and maybe stop recording.
I have one question, maybe a bit basic. So, I mean, I understand that these neural tangent kernels are tools to look at what happens during training and to make predictions about limits of neural networks and then also of quantum models. But I don't I didn't really understand to which extent is this result useful, or can this result be used to actually say something about practical training, or is it more something that says make statements about limit, like the large parameter limit?
So you could do the following. It's a practical statement. For instance, because we are able to compute the neural tangent kernel analytically actually before your training, and then because those are already known formulas, and then for an arbitrary and the answers, you could just put in your answers into the Mathematica, and it will compute you a number, and then you could just diagonalize the circuit. That diagonalizes the kernel and try to take a look on how it decays. And the larger the eigenvalue of the kernel is, the faster it will decay and converge. So that is something you could already do before your training without taking any limit. You could just take some random initialization of your variable and then try to evaluate the value of this kernel. And then that is something people can call it like pre-learning criteria for your quality of your rational answers. And using this way, you are able to, find if your rational answers is good or not, and before any training, because the training optimization kind of task is kind of costed, but this kind of calculations is some analytic calculation you could do before.
But once you first of all, when you do this, you need to be in some sense in a large width limit, right? Because otherwise
no. You could do it at any time. You don't need to do it in a large width limit. So you can just take a random setup of variables theta that you think that makes sense during your gradient descent process. Don't take any limits. Just try to compute the neural tangent kernels. And then if you're assuming your rational angle are in some range, and then your neural tangent kernel will tells you something about the convergence. It is a convergence property at the locally at the given rational angle theta for each setup of theta, right? And then in that case, you are able to already tell, that tells you that locally, if it converges at this point, how good it will converge. And then in order to save time, and you are able to, go to the region of your trainable parameters where your rational angle has some certain value, and then it will converge faster, or some other architecture design that you could have, and will guarantee you, faster convergence. And also you could try to prove some bounds about the convergence by, say, arbitrary value of your rational angle theta, and then that will just directly tell you that some bounds on the possible decay property. For any possible theta in your architecture, you are able to derive some analytic results about if it converge, how fast maximally it could converge. So that is something you could already do, and directly from those formulas. So another idea is that as long as you know where you are expanding, for instance, if you are taking this lazy training limit, and then you have some rational angle theta, you expand it around that, where you assume you are around a local minima, and then in that case, you just plug this value in, and around that value, you already have the exponential convergence. I think I already pointed out those are three practical usage of the rational of this neural tangent kernel theory in rational circuit actually before your training. So you don't need to do any sort of training. You just need to start to compute. As long as you give me your answers, I could evaluate how good it could be.
But then, could you also turn this game around and say, given from, there's in some sense there's a map from ansatz or initialization to the spectrum of the neural tangent kernel.
Right.
So you could try to turn this around and say, okay,
yeah.
from I want to be able to pick good initializations using this map.
Right. So there are people study this also in the classical setting, and this is basically a inverse question on if I correctly understand, and what is the spectrum will be, and for some answers, and if I want to have a good spectrum, and which kind of answers we use, and this is kind of a inverse and the original problem that you would you could from the both sides.
Yeah. Yeah, sounds interesting.
Interesting. Thanks. That's
yeah. So